Welcome back. Let's practice working with multivariable functions. All right, so here's our first example. We're going to begin by evaluating multivariable functions. Specifically for this problem, we want to evaluate the function at each ordered pair, and our multivariable function is f of xy is equal to x times sine y, okay? And so this multivariable function is a function of two independent variables, that being x and y. And so to evaluate this function or get an output value, we will have to plug in both an x value and a y value. And so that's what we are given with these ordered pairs. Starting with part A, we have the ordered pair of 2 pi divided by 4. If we evaluate the multivariable function at this ordered pair, here's what we'll get. We'll have f of 2 pi divided by 4, right? 2 is the x value, and pi divided by 4 is the y value. So what we'll do is replace the x in this function with 2, and replace the y with pi divided by 4. So we'll have 2 times sine of pi divided by 4. Now sine of pi divided by 4 is the square root of 2 divided by 2. So this is equal to 2 times the square root of 2 divided by 2. And so then those 2's cancel out, just leaving us with an output value of the square root of 2. And so that is the value on the function for this ordered pair from part A. Now let's do part B. Let's plug in 7, 0 into this function. So we're going to have f of 7, 0. And so 7 is the x value. We'll plug it in for this x. And 0 is the y value, so we'll plug it in for this y. So we'll have 7 times sine of 0. Now sine of 0 is 0, so this is equal to 7 times 0, which is 0. And so 0 is the value on this function at this ordered pair. All right, so that's part B. Now let's move on to the last part, part C. For our final ordered pair, we have negative 3 pi divided by 2. So if we plug that into the function, or evaluate our function at that ordered pair, we'll have f of negative 3 pi divided by 2. This time around, negative 3 is the x value, so we'll plug that in for this x. And pi divided by 2 is the y value, so we'll plug it in for this y. So altogether, we'll have negative 3 times sine of pi divided by 2. Now sine of pi divided by 2 is equal to 1, so this is equal to negative 3 times 1, which is negative 3. And so negative 3 is the value of this multivariable function at this ordered pair. And so that's it. We are now done. We have evaluated this function at each of these ordered pairs. It's really no different than plugging values into a single variable function. It's just that instead of plugging in a single value for x, we now also have a y value to plug in as well. Let's take a look at another example. Here we once again have a multivariable function that we want to evaluate at different input values, but as you'll notice, this multivariable function has 3 independent variables, x, y, and z. So when we evaluate this function, we're going to evaluate it at sets of ordered triples, okay? We want to evaluate this function at each set of an x value, y value, and z value. And our function f of x, y, z is equal to the square root of x plus y plus z. So in each case, we're going to be taking the x, y, and z values, adding them together, and then taking the square root of that sum. All right, so let's start with the first ordered triple here. If we're going to plug in 0, 3, 6 into our function, here's what we'll get. F of 0, 3, 6 is equal to the square root of 0 plus 3 plus 6. And 0 plus 3 is 3, plus 6 is 9, so this is equal to the square root of 9, which is equal to 3. And so 3 is the value on this multivariable function at this ordered triple. Now let's go to the next one here for part B. We have 4, 6, 2. Let's plug that into the function. So we'll have f of 4, 6, 2. Once again, you want to plug in each of those values for x, y, and z. Last time 0 was x, 3 was y, and 6 was z, but now 4 is x, 6 is y, and 2 is z. All right, so we get the square root of 4 plus 6 plus 2. 4 plus 6 is 10, plus 2 is 12, so we get the square root of 12, which we can simplify a little bit. 12 has a factor that is a perfect square, that being 4. This is equal to the square root of 4 times 3, right? 4 times 3 is 12, and the square root of 4 is 2. So you could pull that out and have 2 square roots of 3. That would be the value on this multivariable function at this ordered triple. Okay, so now let's move on to part C, our final ordered triple, where we have 10, -4, and -3. So 10 is the x value, -4 is the y value, and -3 is the z value. And so if we evaluate it on our function, we'll have f of 10, -4, -3, which will be equal to the square root of 10 plus -4 plus -3. Now 10 plus -4 is 10 minus 4, which is 6. And then you have plus -3, so you're subtracting 3, and 6 minus 3 is 3. So what we get from this is the square root of 3. That is the output value for this multivariable function at this ordered triple. All right, and so that's it. Once again, evaluating multivariable functions is really not all that different from single variable functions. You just have to keep straight which values you're plugging in for x, y, and z. Let's take a look at a different example. Next up, we have given the functions below, find the following. And we've been given f of xy is equal to x times y, g of xy is equal to x times the natural log of y, and h of x is equal to the square root of x. All right, so we've been given two multivariable functions, specifically functions of two independent variables, and we've been given one single variable function. We're going to use this later on in this example because there are multiple parts, but we're just looking at the first two parts here. What we're going to be finding are combinations of functions, right? This notation here wants us to find the function that is the sum of f and g, right? This is f plus g of xy. So to get this function, what we have to do is add f of xy and g of xy. So if we do that here, we'll have xy, which is f of xy, and then add that to g of xy, which is x times the natural log of y. Now you can simplify this a little bit. Both of these terms have a common factor of x that we can pull out. So if you do that, you'll have x times y plus the natural log of y. And that right there would be the final answer for part A. That is the combination of these two functions using addition. But now for part B, we want to use subtraction. We have the function f minus g of xy. So to get that function, we need to subtract g from f. So we'll have xy minus x times the natural log of y. And then once again, we can simplify this. Both of these two terms have a common factor of x. So we can pull that out and have x times y minus the natural log of y. That is the final answer for part B. That is the combination of f and g where we are using subtraction, specifically f minus g. Next up, we want to find the combination of these two functions where we're using multiplication. We want to find the function f times g of xy. So in this case, we're going to be multiplying f by g. So this will be equal to xy multiplied by x times the natural log of y. And we can simplify this. We can combine those x's. X times x is x squared. So you could rewrite this to be x squared times y times the natural log of y. And that would be the final answer. That would be the combination of these two functions using multiplication. Then moving on to our next function here, we want to find the combination of these two functions using division. We want to find f divided by g of xy. So we're going to take f of xy and divide it by g of xy. So that will look like this. We'll have xy divided by x times the natural log of y. Now, once again, we can simplify this. We have a common factor of x in the numerator and denominator that can be canceled out. So let's do that here. Cross those out, and you're just left with y divided by the natural log of y. And that is the final answer for that function. That is the combination of f and g using division. And then finally, for part E, this function that we want to find here is a composite function. Specifically, we want to find the composite function h of f of xy. So what this means is we're going to take our single variable function, h of x, and plug f, our multivariable function, into it. That's what this notation is telling us. H is the outside function, f is the inside function. Okay, so here's what we're going to get. H of x is the square root of x. So when we plug in f into this function, we're going to replace x with that function, which is x times y. Okay, we're replacing every x with this function, so we're going to substitute xy in for x. All right, really what we're doing here is we're taking h and plugging in f of xy, which will be equal to the square root of x times y. And then just to write it as one solid color here, that is the final answer, the square root of x times y, is the composite function h of f. Okay, and that's it for this example. We have now found all the different combination functions as well as this composite function. And so with that, we are done with sort of the oddball questions regarding multivariable functions. Now what we're going to do for the rest of the examples is focus on determining the domain and range of a multivariable function, as well as actually graph the domain. So let's take a look. For this example, we want to find the domain and range, and then graph the domain. And we're given a multivariable function, f of xy is equal to e to the power of xy. Okay, so first of all, you want to make sure you know how many independent variables you're working with. In this case, there are two of them. You know that because they are listed inside the parentheses for the function. In this case, we have x and y. So this is a multivariable function of two independent variables, which means it represents a surface in 3 dimensions. All right, the graph of your function is always 1 dimension higher than the number of independent variables. So this represents a surface, and that surface will have a domain in 2 dimensions. Okay, you will always have a dimension for each independent variable in your domain. That will become important later on when we go to graph the domain. But for now, let's actually try to determine what the domain of this function is, right? What are all the possible input values for this function? Are there any restrictions on what we can plug in for x or y in this function? And if you look at what we have here, e to the power of xy, that is an exponential function, and there's really no restrictions on what you can plug in for x and y, right? You can plug in 0 for those two values, that's fine. You can plug in negative values, you can plug in positive values. Anything is going to work here. There's no x or y value that you can plug in that will make this function undefined, which is normally what you're looking for, right? When you're determining the domain of a function, you want to exclude any input values that are going to cause the function to be undefined, to give you an undefined output value. All right, so there are no restrictions here. And so because of that, the domain for x and y would be all real numbers. And so here's how we write that out. To represent the domain of a multivariable function, we use set notation. So we're going to write it like this. The domain is a set of all x and y values such that x belongs to the real numbers and y belongs to the real numbers. Okay, this little curved e is the Greek letter epsilon. That just means that whatever is written before it belongs to the set after it, and this fancy R that I drew represents the set of all real numbers. Okay, so this is one way that you could write it. Both x and y can be any real number, but a more compact way to write it would be like this. You can say that we're working with all values of x, y that belong to R squared, which is not just the set of all real numbers, but the set of all ordered pairs of real numbers, which is exactly what we're looking at here, ordered pairs of x, y. All right, essentially R squared just represents all the different points that you could pick in the xy plane. That's how I like to think about it. So that is the domain. That's how we'd represent the domain of this multivariable function. But what about the range? What are the possible output values or z values? Technically, you could rewrite this function to be z equals e to the power of xy, right? Z would be the dependent variable for this function. So what are the possible values of z? What can you get or not get as an output for this function? Well, once again, we do have an exponential function. So if you're thinking about what happens to an exponential function, it never outputs a negative value, right? Anything you plug in for x or y here, even if that exponent becomes negative, will still result in a positive value. E to the power of anything is going to be a positive number. And so that can be any number in the positive direction, but the bottom line here is that z can only be positive. You're never going to get a negative output value. And you're also never going to get 0, right? An exponential function will never be equal to 0. So the range here is all positive values greater than 0. And here's how I would write that out. The range is the set of all z values such that z is greater than 0. That's how I would write it. That would be my answer for the range. Once again, we came to that conclusion because that exponential function can't output negative values, or 0 for that matter. Okay, so we found the domain and range, but now we want to graph the domain that we found. And so like I said at the beginning of this problem, we have two independent variables, right, x and y, and so our domain will be graphed in 2 dimensions, which makes sense because we just said right here that the domain is all values of x, y belonging to R squared, which is the set of all ordered pairs, which by definition is in 2D. All right, so we're going to graph our domain in the xy plane. And so go ahead and draw yourself an xy plane just like this. And then what you want to do is shade in all of the possible values of x and y. Now, in this case, that's everything, right? There is no restriction on our input values, so we would shade in the entire xy plane. Or at least that's what we're going to try to show here. Technically, the xy plane extends forever in all directions, so we can't shade in everything, but we can try to represent that as best as we can with our drawing here. So all you have to do is draw your xy plane and then simply shade it all in. All of those points of xy are part of the domain. Okay, and that should make sense. If you were to take a look at the actual graph of the surface represented by this multivariable function, I'll put a 3D render up here on the screen for you. You can clearly see that the entire xy plane is in play, right? You can pick any set of x and y coordinates and plug those into the function and get an output for the function, or a z value. And also, while the surface is on the screen here, notice that the surface never goes below the xy plane, right? All of the z values are positive, which is exactly what we found for the range, right? We said that our range was only for z values greater than 0. And so the surface here never touches the xy plane, and it also never goes below it. So hopefully you can see that our answers make sense. Okay, but with that, that is it for this example. Let's take a look at another one. Here we once again want to find the domain and range of our given function, and then we also want to graph the domain. And our multivariable function, this time around, is f of xy is equal to x plus y divided by x times y. Okay, so once again, we have a multivariable function of two independent variables. So this does represent the graph of a surface, which is in 3 dimensions, and the domain will count for the independent variables x and y. So the domain is in 2 dimensions. And so speaking of the domain, let's try to figure it out. What input values make sense for x and y? Are there any values of x and y that when we plug them into the function result in an undefined value? And well, looking at the function here, it is a rational function, meaning it's a fraction. We have a numerator and denominator. And something that you always want to be checking is, can the denominator be 0? Because if it is 0, then you have a problem. You can't divide by 0. That's an undefined value. And so that might affect what we include in the domain. And so what you want to do is take that denominator and set it equal to 0, or write out that it can't be equal to 0, right? In this case, we do not want x times y to be equal to 0. That is the restriction on the input for this function. We can plug anything we like into the numerator, that's not going to cause a problem, but if the denominator is 0, that would be a problem. And so when does this happen? When does x times y equal 0? Well, it's going to be 0 when either x equals 0 or y equals 0, right? If x is 0, it doesn't matter what y is, 0 times anything will be 0. And if y is 0, it doesn't matter what x is, because anything times 0 is 0. So from this, we get two different restrictions. X cannot be equal to 0, and y cannot be equal to 0. That's what we learn here. So the domain of our function is the set of all x, y values such that x is not equal to 0 and y is not equal to 0. That is how we would represent the domain for this function. All other values of x and y are fine as long as neither of them are 0. And so that would be the domain of this function. But what about the range? What output values make sense for this function? Well, all of them, right? Even though x and y themselves can't be 0, the output here still could be 0 if x and y are the opposites of each other. Let's say that x is 3 and y is negative 3. 3 plus negative 3 is 0, and 0 divided by those two numbers multiplied by each other would still be 0. And so you still could get 0 as an output for this function, and you could also get all positive numbers and all negative numbers. Nothing here is going to restrict the range. The range is going to be all real numbers for z. Okay, because once again, you could write the function using the dependent variable z. You could say that z is equal to x plus y divided by xy. And so when we're talking about the range, we're talking about those values of z that are possible. And in this case, it's going to be all real numbers. All right, so I'd represent that like this. The range is the set of all values of z such that z belongs to the real numbers. You could also write it as z less than positive infinity and z greater than negative infinity, but I think it's easier to just write that z belongs to the set of all real numbers. All right, so that would be the range here for this multivariable function. And so now we have determined both the domain and range, but now we want to graph the domain. So let's do that. Once again, our domain will be in 2 dimensions because we're working with 2 independent variables. So you need an axis for each of those independent variables. We need an x and y axis, which gives us the xy plane. So make sure to draw yourself an xy plane. But now how do we actually graph the domain here? Well, remember, you want to shade in all of the different sets of x and y values that can be plugged into this function. So that's everything except where x equals 0 and y equals 0. In other words, everything but the y-axis and the x-axis. So what you want to do is shade in the xy plane, but don't shade in the axes. Now I'm going to over-exaggerate a little bit. I'm going to get purposely not too close to those axes. So I'm going to shade it in like this, just to really emphasize the point that we're not including any points that have y equals 0 or x equals 0. Okay, so this is how you would shade in the domain for this multivariable function. All right, and once again, to help you get a good visual of what we're doing here, here's a 3D render of this specific multivariable function we're working with. And you can see, if you were to look at this surface from the top down, so you're looking straight at the xy plane, that the surface does not have any points that touch the x or y axis, right? The x coordinate and the y coordinate are never 0 for any of the points on the surface. The surface is broken up by the x and y axes. Okay, so this is just a nice way to see that our answer does make sense. Next up, we want to find the domain and range of this multivariable function, as well as graph its domain. We have f of xy is equal to the square root of 9 minus x squared minus 9y squared. Okay, so once again, we do have a multivariable function with 2 independent variables, x and y. So this does represent a surface in 3D with a 2D domain. And so let's try to determine what that domain is. So you want to look at this function and ask yourself, are there any values of x and y that would cause this function to be undefined? And something that you should see here is that we do have a square root, and you always want what's inside a square root to be positive, right? You don't want to take the square root of a negative number because that gives you an imaginary number, which is not a real number, and we're only working with real numbers here. So the restriction that we have here for this function is that the contents of this square root must be greater than or equal to 0, right? It's okay if this equals 0 because the square root of 0 is 0. That's fine. But anything smaller than 0 would not be good. So we want 9 minus x squared minus 9y squared to be greater than or equal to 0. All right. Now, if we rewrite this a little bit to make it look a little bit nicer, what we can do is add x squared and 9y squared to both sides of the inequality and have 9 is greater than or equal to x squared plus 9y squared. And if you imagine for a second that that inequality sign was actually an equal sign, what we'd have here is the equation of an ellipse, right? We can get it in the standard form if we divide both sides by 9. If you do that, you'll get 1 greater than or equal to x squared divided by 9 plus y squared. That's really what our restriction is here. And when we go to actually graph the domain, you will see that this directly translates to an ellipse in the xy plane where all the points that we can plug into this function are contained within that ellipse. All right, so we'll get to that in a second, but for now, let's just write down what the domain is. The domain is the set of all xy values such that x squared divided by 9 plus y squared is less than or equal to 1. Okay, I just wrote this same restriction but reversed the sides of the inequality. So I wrote this half first, but then remember that it would be less than or equal to 1 since 1 is greater than or equal to those two terms. Okay, so just make sure to flip that sign if you're flipping the sides of the inequality like I did here. But that would be the domain. We can use any values of x and y that we like as long as x squared divided by 9 plus y squared is less than or equal to 1. So that's our domain, but what about the range? And this can be a little bit tricky because there actually is going to be a restriction here on what output values we could get because there is an upper bound for our input values, right? Whatever x squared divided by 9 plus y squared is, it has to be less than or equal to 1. It can't be bigger than that. Or really, if we go back to this step, x squared plus 9y squared can't be bigger than 9. That is the largest possible value we should get for what is going to be subtracted from 9 in this square root. that ensures that this will never be a negative number, right? The biggest number that we should be subtracting from 9 is 9 so that you get 0, and the square root of 0 is 0. So that's going to be the smallest value possible, right? That's going to be the smallest output value because you can't get a negative number from a square root. So the lower bound for the range is 0. So I'm going to write that down here. The range is all values of z such that 0 is less than or equal to z, meaning that z is greater than or equal to 0. It's going to at least be that value. But is there an upper bound? Is there a value that z can't be bigger than? Well, there is. Because if you go back to our restriction again, notice that both x and y are being squared. Because of that, if you plug in negative values for x and y, they're going to be made positive. All right, so you're going to have positive values after those squares are done, and then you're dividing x squared by 9 and adding those two values together. There's no possibility that that result can be negative. All right, so really we could have had another restriction here. We know that this expression will be greater than or equal to 0. It can't be negative because of those squares and we're adding everything together. We're always going to get a positive result. So what we find here is that the smallest this value can be is 0. So if you had 0 for this expression here that you're subtracting from 9, you would have 9 minus 0, which is just 9, and so the square root of 9, which is 3, would be the largest possible value that you could get. All right, so z has to be less than or equal to 3. It's a small range, but those are all the possible values for the output z for this function. Okay, but now what we're going to do is graph this domain. And so once again, it will be in 2 dimensions. We have to account for both x and y. So draw yourself an xy plane, and then what we want to do is graph what we have found for this domain. As I mentioned earlier, this inequality here is in the form of an ellipse, right? We have x squared divided by 9 plus y squared less than or equal to 1, which if that inequality sign was an equal sign, you would recognize this to be the equation of an ellipse. It's not a circle because x squared is being divided by a constant. It is in fact an ellipse, particularly an ellipse that is centered at the origin and will reach out to a radius of 1 in the y direction because y squared is being divided by 1 squared technically. And in the x direction, it would be a radius of 3 because x squared is being divided by 9 and the square root of 9 is 3. All right, so we do have an ellipse here and we're looking at intercepts of y equals plus or minus 1 and x equals plus or minus 3. And so let's graph that ellipse over here. We want to plot a point at y equals 1 and negative 1 and x equals 3 and negative 3. And so connecting those intercepts, we'll get an ellipse like this. And then the question is, do we shade all the points inside that ellipse or outside that ellipse to represent all the points that could be plugged into this function? Well, looking at our inequality here, this expression must be less than or equal to 1, which means we're looking at values inside that ellipse, okay? If it was greater than or equal to 1, then you would be looking at everything outside. But since it's less than or equal to 1, we're looking at the inside values. And so what you want to do is shade in this ellipse, and that will represent the domain of the multivariable function. Any pair of x and y coordinates inside this ellipse can be plugged into the multivariable function and get a real output for z. Okay, and then just to help you visualize again, here's a 3D render of the surface represented by our multivariable function. You can see that it is half of an ellipsoid, which makes sense given what we just found for our domain. And so if you were to look at this surface from the top down, you will see that all of the points in the xy plane that give a z value for the surface are contained within an ellipse, the same exact ellipse that we graphed in our xy plane right here. Okay? Let's take a look at another example. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. We once again want to find the domain and range, as well as graph the domain for this multivariable function. We have f of xy is equal to the natural log of 5 minus x minus y. Okay, so once again, we do have a multivariable function of two independent variables, x and y, so this does represent a surface in 3 dimensions and has a 2-dimensional domain. And so let's start by determining the domain here. If we're thinking about what values of x and y we can plug into this function, or if there are any values that would result in an undefined value, something of importance here is the fact that we are working with a natural log function. And remember that the input for the natural log function cannot be negative and it can't be 0. All right, so the restriction here on our x and y values is that the inside of this natural log function must be greater than 0, right? 5 minus x minus y must be greater than 0. If it's less than 0 or equal to 0, you'll get an undefined value for the natural log function. It's only defined for positive inputs. All right, now typically what I like to do is solve for y in these restrictions. It just makes it easier when we go to graph our domain later. So what I want to do here is solve for y. I'm going to add it to both sides of the equation. So that would give us 5 minus x is greater than y. And then I'm going to write it in the reverse order. Y is less than 5 minus x. Or if you want, you could write that negative x first. That's also going to be helpful for when we go to graph the domain. So I'll write negative x plus 5. It's just going to help you see what this represents graphically in the xy plane. And we'll get to that in a second. For now, let's just finalize our domain. The domain for this multivariable function is a set of all x and y values such that y is less than negative x plus 5. That is the only restriction on this function. We just have to make sure our input values are greater than 0 for that natural log function, which translates to this restriction right here. Okay, so that's the domain. But what about the range of this multivariable function? Well, there really is no restriction on that, because even though you can't input negative values into the natural log function, or you can't input 0 either, you still can get output values that are negative, and you can get an output of 0 from the natural log function. The natural log function has a range of all real numbers. And so the same is going to be true here. It doesn't matter what values of x and y you plug in, as long as they are on the domain, the output of this multivariable function could be any value of z. All right, so the range here is the set of all values of z such that z belongs to the real numbers. All right, or once again, you could write that as z greater than negative infinity, but less than positive infinity. But this is the way that I prefer to write it. Okay, so now we have the domain and range for this multivariable function, but now let's graph the domain. Make sure to include both an x and y axis, because the domain is in terms of x and y. And so what we want to do is graph this inequality. Y is less than negative x plus 5. That's going to tell us all the different pairs of x and y that we could plug into this function. So ignoring that inequality sign for a second, imagine that this is y equals negative x plus 5. That's just a linear equation, right? That represents a line with a slope of -1 and a y-intercept of 5. All right, so to our graph, if this right here is y equals 5, which would make this x equals 5 and so on, this is a -5, -5, our line would cross through that y-intercept, and it would have a slope of -1, so the line would be sloped in this direction. Okay, but I am going to draw that line as a dotted line because this is just a less than sign. It's not a less than or equal sign. We are just going to be looking at y values less than this line. Okay, you have to remember how to graph inequalities from algebra for this. Maybe it's been some time since you've done that, but it's really not too difficult. I'm going to draw a dotted line, but then we are looking at y values less than that. So that would be everything below this line, okay? So our domain would be all of the points below this line in the xy plane. So you want to shade in this region right here. Feel free to go right up to that dotted line because it is not included, right? The dotted line signifies that. So you can shade right up to it, and there you have it. This represents the domain of this multivariable function. And it makes sense. If you were to look at the graph of the surface for this function, I'll put up a 3D render once again. You can see, for one thing, that there is no restriction on the output for z. It's going to include all positive and negative values. But then if you were to look at the function from the top down, so you're looking at the xy plane, you can see that the graph of our domain is accurate. There are no points above the line that we drew that result in an output for z. Okay, the entire surface is made up of points that do not have a pair of xy coordinates from above that line. Let's move on to the next example. Next up, we want to find the domain and range, as well as graph the domain. For this multivariable function, we have f of xy is equal to arc cosine of x plus y. Okay, so just like with our previous examples, this multivariable function has two independent variables, x and y, so this does represent a surface in 3D with a two-dimensional domain. And so to figure out that domain, we have to think about what input values make sense for this function. Are there any values of x and y that are going to cause this function to be undefined? And this one can be a little bit tricky at first, at least if you don't remember how the inverse trig functions are defined, because we are working with the inverse cosine function here. That's what this is. Arc cosine is the inverse cosine function. You might also be familiar with this notation. So this is what we're working with here. And the arc cosine function does have a unique domain. In particular, the input values for arc cosine will always be between -1 and 1, including those two endpoints. All right, so remember, for arc cosine, the input is on this interval from -1 to 1. That is true for the arc cosine function. So whatever we plug in here, whatever x plus y is, has to be between those two values, or can also be those two values. Okay, so here's our restriction. X plus y must be less than or equal to 1, but greater than or equal to -1. That would be our restriction for the domain. So let's write that out. The domain would be the set of all xy values such that -1 is less than or equal to x plus y, which is less than or equal to 1. Okay, so that is the domain. But then what about the range? Well, that's also going to depend on the arc cosine function itself. And if you are familiar with the definition of the inverse cosine function, yes, the input is from -1 to 1, but the output is from 0 to pi. All right, if you don't remember, this is what the graph of arc cosine looks like. It's a curve that does not go on forever. It just looks something like this, where this right here is pi divided by 2, this right here is pi, and this, of course, is the value of 0. So there you can see the output values from 0 to pi, and then this right here is 1 and -1. So there's the input values from -1 to 1. That is the graph of arc cosine, and that's still going to be true here. Even though we're working with a multivariable function, the output of arc cosine is still going to remain the same. It's still going to be values between 0 and pi. So the range would be the set of all values of z such that 0 is less than or equal to z, which is less than or equal to pi. All right, it can output any values of z between 0 and pi, including those two values. And so that would be the range of this function. Now, let's actually go ahead and graph the domain that we found. You will want to draw yourself an xy plane because there are two independent variables for this function. We need an axis for each of them to graph the domain. And to help us graph this, I'm going to split up this inequality into two statements. In particular, I'm going to split it up like this. We're going to have -1 less than or equal to x plus y. That's this portion of this statement. And then we'll write down this portion as well. We know that x plus y must be less than or equal to 1. Now in each case, to help me graph these two statements, I want to get each of these in a form where y is isolated. All right, so for this one, we just have to subtract x from both sides. So we'll have y less than or equal to -x plus 1. That's one of our restrictions that we can graph pretty easily. And then for this one over here, I'm going to subtract x from both sides. And what you would get is y greater than or equal to -x minus 1. Okay, so I subtracted x from both sides and flipped the two sides of the inequality. So this is what you would get. And now we have two inequalities that we know how to graph. If you ignore those inequality signs and view them as equal signs, we just have equations of two different lines. So what we want to do is graph them, and we will have solid lines this time around because the signs are greater than or equal to and less than or equal to. But then we're going to be shading in the region that those two inequalities have in common. Okay, so for now, let's just draw the lines. For this one, we have -x minus 1. So if this right here is y equals 1, this is -1, this is x equals 1, and x equals -1. This line will have a slope of -1, and it will cross through the y-axis at -1, okay? So that would be this line right here. That right there is y equals -x minus 1. And then let's graph this one as well. This would represent a line with a slope of -1 as well, but the y-intercept is +1. So that line would look something like this. Okay, so that line is y equals -x plus 1. But now let's actually take care of the fact that these are inequality signs. For this line, which is this one right here, we're looking at y values greater than or equal to the line. So that would be all values above this line. And then for this one, we're looking at y less than or equal to that line. So we're looking at all the values below it. So the shared region between these two inequalities is all the points between those two lines. Okay, so just to make myself clear here, this inequality, if you were to graph that, would give you all of these points up here, and then this inequality would give you all the points below this line. So that would be everything right here. But the overlap is everything between those two lines, and so that's the actual domain. So that's what we want to shade in here. The domain for our surface is everything between those two lines. And so if you were to look at the graph of the surface of this multivariable function, here's a 3D render of it, you'll see the exact same domain that we just graphed. Looking at the surface from the top down, so you're looking at the xy plane, you can see that the entire surface is contained between those two lines. All the input values for x and y are points within that strip along the xy plane between those two lines that we graphed. Okay, so that's it for this example. Let's move on to the next one. Here we want to find the domain and range, as well as graph the domain of this multivariable function. F of xy is equal to 1 divided by the natural log of x squared plus y plus 1. And this one's kind of a tricky one, but before we talk about the domain too closely, first of all, notice that this is a multivariable function of two independent variables. We have x and y, and so it does represent a surface in 3 dimensions, and its domain will be in 2 dimensions. Okay, so now what we want to do is ask ourselves what values of x and y make sense. Is there any way that this function could be undefined for any values of x or y? And for one thing, we do have a rational expression here where the denominator cannot be 0, and so you have to ask yourself what would make the natural log of something be equal to 0, and the answer is the natural log of 1 is equal to 0, right? So what that means is that the contents of the natural log function here cannot be equal to 1, otherwise you'll have the natural log of 1, which is 0, right? We know that the natural log of 1 equals 0, so that tells us that x squared plus y plus 1 cannot be equal to 1. That's one of our restrictions. But we can simplify it a little bit. If you subtract this 1 from both sides, you would have x squared plus y cannot equal 0, right? Both of those 1s would be gone. And then subtracting x squared from both sides, you'd have y cannot be equal to negative x squared. Okay, so that's one restriction, but it's not the only restriction. Because remember, the natural log function cannot have any negative inputs or an input of 0. The input for the natural log function has to be positive. So not only can the contents of the natural log function not be equal to 1, but they also have to be bigger than 0. All right, so we're going to have another restriction that x squared plus y plus 1 must be greater than 0. And so then I want to solve for y once again. So I'm going to subtract 1 and x squared from both sides, giving us this: y must be greater than negative x squared minus 1. Okay, so those are our two restrictions here. The domain of this multivariable function will be all values of x and y such that y is not equal to negative x squared, comma, y is greater than negative x squared minus 1. Okay, you want to include both of those restrictions in the domain. Okay, so that's the domain, but now what about the range? What would the range of this multivariable function be? Well, pretty much anything, right? Except for 0. The natural log function can output negative and positive values, so this expression could be positive or negative, so that would include the majority of the set of real numbers, but the only thing it can't be is 0, because the numerator is always 1, that's never changing, and 1 divided by anything will never be 0, because you can't divide by 0, that's not going to be equal to 0, and there's nothing else that could possibly happen to make this equal 0. So the only output value that can't happen here is 0. everything else is on the table. Okay, so the range here is all values of z such that z is not equal to 0. That is the only value of z that is not possible for the range. Okay, so now we have both the domain and range. Now let's graph the domain. And to graph our domain this time around, we still need to use the xy plane because x and y are the independent variables, but we have two different restrictions that we need to account for. Let's start with y does not equal negative x squared. Basically, what that's telling us is that we're not going to be using any points for the parabola that opens in the negative y direction, right? Y equals negative x squared would be a parabola that opens downward. Okay, so if this is y equals 1, this is y equals negative 1, x equals 1, and x equals negative 1. The parabola y equals negative x squared would look something like this. Okay, that is y equals negative x squared, and any point along that parabola is not included in the domain. So when we shade in our domain at the end, leave a little bit of space between your shaded region and this curve. You don't want to touch this parabola in any way. Okay, we'll come back to that, but let's graph our other restriction. We have y greater than negative x squared minus 1. So really this would also be a parabola, except it's shifted down 1 unit in the y direction. Okay, that's what this negative 1 tells us. We're taking negative x squared, which is this parabola, and shifting it down 1 unit. Okay, so we'd also have a parabola like this, but I am drawing it as a dotted line because we're not including it. Okay, this is an equality of just greater than, not greater than or equal to. So I will draw a dotted line. That way we can shade up to that line, but we're not including it. Or at least this is the way I'm going to go about it. Technically, I guess you could also draw this parabola as a dotted line because you wouldn't be including it, but I think it'll make more sense visually when we actually go to shade in this region. You'll see what I mean in just a second, because what we're going to do now is actually shade this in. This inequality says we're looking at all values of y greater than that parabola, right? So the shaded region would be everything above this parabola, but you have to remember not to include any points along this parabola. So here's what this is going to look like. We're actually going to shade in this region up to that parabola. All right, so we're starting at the lower parabola here, but then we're not going to touch that y equals negative x squared. So this is part of our shaded region, and then we're going to have everything else above that parabola. Okay, that would be the domain for this multivariable function. It's going to be all points or all coordinates of x and y that are within this shaded region. Anything that is along that parabola, we don't want to use, specifically the parabola negative x squared, as well as anything below this other parabola, negative x squared minus 1, which I never labeled. I guess I'll do that here. This is negative x squared minus 1, or y equals negative x squared minus 1. But regardless, that is our domain. It's pretty complicated, but if you were to take a look at the actual surface represented by this function, for one thing, you can see that the range does in fact not include 0. The z value is never 0 for that surface. But then if you were to look at the surface from the top down, so that you're looking at the xy plane, you can see exactly what we just graphed. There are no points that make up that surface that are along that parabola of negative x squared or below that other parabola, negative x squared minus 1. Okay, all the pairs of xy coordinates that give a z value for the surface are contained everywhere else within the xy plane. So the graph of our domain here is correct. It does make sense. Okay, so that's it for this example. Let's take a look at a slightly different one. For this example, we still want to find the domain and range of our multivariable function and graph its domain, except now we have a function of 3 independent variables, right? We have f of xyz equals xyz. And so this function represents a 4-dimensional shape. So we're not going to be able to graph this function in any way. We're not going to be able to visualize what it represents, but we will be able to graph its domain because the domain will always be 1 dimension less than the dimensions of the actual graph, okay? There will be 1 dimension for each independent variable in the domain. So the domain of this function will be in 3 dimensions. So we can graph it. And so looking at this function of 3 independent variables, are there any inputs for x, y, or z that would cause an undefined value? Well, no, right? This is a very simple function, x times y times z. You can plug anything in that you'd like, and you'd be good to go. You're never going to get an undefined value for this function. So this one's pretty simple. There's no restrictions, and so the domain is the set of all values x, y, and z such that X belongs to the real numbers, Y belongs to the real numbers, and Z belongs to the real numbers. Okay, so you could write that like this, but it's a little bit cumbersome to do it like this, but this would be true. Or you could write it like this. This is the way that I would prefer to do it. Just like we did for 2 dimensions, you can just say that we're including all values of x, y, and z that belong to the set of all ordered triples, or r cubed. That represents all the different points within the 3D coordinate system that could be used for this function. Okay, so that is the domain. But what about the range? We're not going to be using z this time as a dependent variable because z is one of our independent variables. Typically, when we have 3 independent variables, what we use as a dependent variable is w. So you could also rewrite this as w equals xyz. So that's what we're going to be working with for the range here. And just like how there's no restrictions on the domain, there's also going to be no restrictions on the range either. Okay? We can get both positive and negative values from this, as well as 0. If all 3 of these were squared, if we had x squared, y squared, and z squared, then we would have to exclude all the negative output values, but that's not the case here. We can get negative values, so the range would also be all real numbers. So the range here is all values of w such that w belongs to the real numbers. Okay, so that's the range. Now let's actually graph the domain here. And remember that it will be in 3 dimensions because we have 3 independent variables. But there's really nothing for us to graph here because we're including every single point within 3-dimensional space. So this is pretty simple. You just want to shade in your entire 3D coordinate system. All of those points are within the domain of the multivariable function. Okay, so that's it. Let's take a look at one more example for this video. All right, so here's our last example. We once again want to find the domain and range of our given multivariable function, and then also graph its domain. And we have another multivariable function of 3 independent variables. We have f of x, y, z is equal to the square root of 4 minus x squared minus y squared divided by z minus 2. Okay, and so once again, this function represents some 4-dimensional shape that we can't graph, but it will have a domain in 3 dimensions that we can graph. And so thinking about the domain for this function, are there any values of x, y, or z that could cause this function to have an undefined value? And well, there's a couple. For one thing, in this denominator here, we know we can't have 0, so you want to set z minus 2 to be not equal to 0, right? So for one thing, z minus 2 cannot be equal to 0, which means that z cannot be equal to 2. We know that for sure. But then in the numerator, we have a square root, so we have to be sure that the input values are greater than or equal to 0. It has to be positive, all right? So that inside part of the square root, 4 minus x squared minus y squared, must be greater than or equal to 0, okay? We can include 0 in this case because the square root of 0 is 0. That's fine. If this was in the denominator, then we couldn't have 0. But since the square root's in the numerator, we can include 0. All right, so from that, if you were to add x squared and y squared to both sides of that inequality, you could rewrite this to be x squared plus y squared must be less than or equal to 4. All right, so those are going to be our 2 restrictions for our values of x, y, and z that can be plugged into this function. All right, so the domain is a set of all values of x, y, and z such that x squared plus y squared is less than or equal to 4 and z does not equal 2. Okay, that's the domain. But now what about the range? Because that seems a little bit tricky this time around. If you're looking at the numerator, it's true that there would be a restriction on what can possibly be outputted by the square root of this expression. And so you might think that we're not going to include all real numbers, but whatever that is going to be divided by z minus 2, which the only thing that can't be is 0. And so you can get any other value from this. Z minus 2 can be some positive number or it can be some negative number. And so whatever value you get up top can be divided by practically any number, meaning you could really get any real number, even 0, because this numerator could be 0 for a particular value of x and y, while z does not have to be equal to 2 at the same time. Okay, so the output here could be anything. In this case, we would say that the range is all the values of w such that w belongs to the set of all real numbers. Okay, so the domain is restricted, but the range can be anything. There are no limitations on the output for this function. All right, so now we have our domain and range. Finally, what we want to do is graph the domain that we found. And just like with the previous example, we are going to be graphing in 3D because we have 3 independent variables. So draw yourself a 3D coordinate system, and then what you want to do is take into account these 2 restrictions. Now remember, we are working in 3 dimensions, so everything here will be graphed in 3 dimensions. For this first statement, we have x squared plus y squared is less than or equal to 4. Normally you would look at that and say, well, that's a circle, but we're talking about 3 dimensions here, so that's not just a circle, it's a cylinder. It's a circle in the xy plane that would be directed along the z-axis. All right, it's a circle with a radius of 2 because the square root of 4 is 2, and then you take that circle and extend it upwards and downwards along the z-axis. All right, so here's what that looks like if this is y equals 2, x equals -2, y equals -2, and x equals +2. Our circle might look something like this, but then we're shooting it out along the z-axis, and so you want to draw some lines parallel to the z-axis, and there would be our cylinder. Not a perfect sketch, but it gets the point across. The domain is going to include all points inside of this cylinder, right? Because we have x squared plus y squared less than or equal to 4. When it's less than or equal to that value, you're looking at the values inside your surface. If it was greater than or equal to 4, then you would be looking at everything outside of it. But that's not what we're looking at here. Okay, so you do want to shade everything inside that cylinder. And of course, that would extend forever in the positive and negative z directions. However, there is one particular part of this cylinder that we don't want to include, and that is where z is equal to 2, right? You can't forget about your other restriction. Let's say that z equals 2 is right here. Z equals 2 would be a plane in the 3D coordinate system, and so what that means is you would not include any points within the 3D coordinate system that have a z coordinate of 2. And so if you imagine that there would be a plane cutting through that value of z, really what we end up excluding is just a thin disk of this cylinder. All right, so I'm just going to draw a thin little disk here at z equals 2. So I'm just going to make it a different color to signify that we're not including that disk at z equals 2, okay? And so to help you better visualize what we just graphed here, here's a 3D render of the domain. Again, this is not the actual surface. The real surface would be in 4 dimensions. What you're looking at here is the domain that we just graphed. The domain of the function is all of the points inside that cylinder except where that plane intersects it, which would just be a thin disk for z equals 2. All right, and so with that, that is it for this example. And this was also the last example for this video. But if you do want to get some more practice with multivariable functions, I do have more examples available on my membership site. So if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.